Hi YouTubers, this is Mr. Lim here, and this is the last video on addition polymerization on polyethene and polytetrafluoroethene. So, this is the boring part where you have to go memorize some stuff about polyethene and polytetrafluoroethene. And I hate memorization. So if you have the access to the OneNote where I put all these notes down, you can just copy from there. Actually, you should watch the video because there's some other stuff in here. But this is pretty boring. Be prepared. So, you need to know about specific properties and uses of a number of polymers. You will have to do your own research because this is not an exhaustive list. These two here are listed specifically in the syllabus, which means that they will be able to ask you questions specifically about these two, and none of us. So hopefully they don't. Okay, so polyethene made from ethene, duh. Okay, there's two types, LDPE or low density, and then high density HDPE. All right. LDPE, reaction conditions. These, memorize these. All right. During the production of LDPE, branching can occur from where the main chain, a side chain, and backbones can be formed. Okay, so what that means is that here's your main chain. Okay, and suddenly from nowhere, a side chain will pop up. And side chains can continue to polymerize and make, long lengths of these side chains out of the main backbone of the carbons, right? And so this carbon keeps on growing in length, and these side chains exist there. All right. So those side chains will make this LDPE low density, and we'll talk about that in a bit. Okay. So branching means that the chains and backbones cannot pack tightly together, and thus there are weaker intermolecular forces than there would be if they were all packed really tight together. So what that means is that, okay, if you could get all of your strands real close to each other, they'd form very strong dispersion forces across the entire rank of chains. Okay, which means that, dispersion forces, the electrons are going to be flying around randomly. They're going to create temporary instantaneous dipoles, which are going to induce temporary instantaneous dipoles in neighboring molecules. And if they're closer, they'll create better temporary instantaneous dipoles. And if you can pack them closer in, you can create better temporary instantaneous dipoles and therefore have a stronger dispersion force. However, because you've got these branches in these side branches in the way, okay, that means that this one here can only get, so close to the next one. All right, and so that distance, that increased distance, means that you have weaker intermolecular forces, and they're going to be low density because there's lots of space in between. And so that's why they're LDPE. And what does that mean for their properties? It means that you're going to have a low density. In fact, the other HDPE has still a low density, but it's a lower density than that. They're pretty they're pretty like weak plastics. Okay, so you use them for films, and they have high impact strength, but that just means you can squash them, and you can squash a plastic bag and it not break. Yeah, useful, but it's not very strong in terms of the other dimensions as well. Right, there's some stuff, memorize that. Memorize it, but just know what it's used for, which is this is what you use it for: plastic bags, containers, blah blah blah, so on and so forth. These three here are the disadvantages of LDPE. So there's poor UV resistance, high gas permeability, which means can't use it as balloons and stuff, and it's flammable, which is not useful. But these are the uses. Oh, I don't understand why those three are there. They should be in the properties. Meh, you get the idea. HDPE. So it's again polyethene, but this time you're using a Ziegler-Natta organometallic catalyst or a Phillips type catalyst, and I have no idea what those are. You can go find them out yourselves. Pressure, temperature stuff, and uses a mixture of hydrogen and ethene to control the chain length, because if you think about it, these chains will continue to grow until they're stopped, and they're stopped by a little bit of hydrogen on the ends, and therefore that controls their chain length. Okay, but that's that. Okay, so branching does not occur. What does a chain look like without branching? That's what a chain looks like without branching. To be honest, there's actually just very small branching. Okay, smaller branching occurs rather than large branching. Okay, and if you have no branching, you can pack them closer together, and as we said about packing them closer together, it means that they'll have stronger dispersion forces, i.e. intermolecular forces, and then have a higher density and have higher strength. So what do we got? Some stuff about HDPE, it's different. This is important, high tensile strength, which means that you can pull them apart and they won't break, which means that you can start using them for like actual stuff that you can, stand on and stuff. So like furniture and stuff. And, it has some stuff. Again, this one, these two here are the disadvantages of HDPE, or their properties. Okay. Yeah, stuff. And this is the uses like crates, bottle caps, blah, 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 that kind of stuff. So you have a look, you watch, you memorize, blah, blah, blah. All right, PTFE, aka Teflon. Okay, so made from tetrafluoroethene, that's why it's called polytetrafluoroethene. And here is a diagram of polytetrafluoroethene. Oh, I didn't realize I have to draw this. Well, let's have a think. If it's made from tetrafluoroethene, what's it going to look like? A whole bunch of fluorines. Oh, I'm so bored of this already. Okay, polytetrafluoroethene. Don't forget the open-ended stuff on polymers. How many repeating units? 2 repeating units. Why are you only drawing 2, not 3? Because I'm lazy. All right, reaction conditions. Yeah, stuff. Here you go. Read that. Oh yeah, this is cool. This very reactive, blows up if you keep it for too long. So you don't keep it very long. You build it on site, you turn it immediately into Teflon on site, and you do that with like, some stuff. Properties, highly thermostable, and you'll notice that this is in Kelvin. So what that's talking about is 60 Kelvin is what, like negative 210 degrees Celsius all the way to 630 Kelvin, which is quick maths, I don't know, like 300 something plus degrees. I don't know. I'm not very good at quick maths. So therefore, it works in a very large range of temperatures. High melting point, highly chemical resistance, electrical insulator, low friction, non-stick. That's why you have Teflon in your pans, and stable under UV radiation. Interesting fact, Teflon is not good for searing steaks. Like even though it's got high temperature resistance, it does, like if you superheat it on a stove and you put your steak on it, like it wrecks the Teflon. So don't do it, and you can't even get your money back. So if you want to cook a nice steak, use a cast iron or a stainless steel pan, because that's what you should be using to sear steaks. Look, life lessons. And uses for PTFE, cable insulation, blah, blah, blah. This is the one that you know the best. Non-stick domestic uses, i.e. on pots and pans. Funnily enough here, it doesn't have like, they put it on the spaceship because they wanted it to be super smooth when coming down through the atmosphere, but like it does that too. That's quite cool. This one's quite cool. They put it in chemical reactors so that because of its high chemical resistance, it doesn't actually get reacted with whatever you're dealing with inside that chemical reaction, even if you're doing it at super high temperatures. Not even super high temperatures, because Teflon does break at like 300 degrees, but like high temperatures. And there's some stuff. Learn that, memorize that. This has been a boring PowerPoint. I'm bored already. Just go memorize some stuff. Adios.